So today I want to talk to you very specifically about the difference between RL, which is reinforcement learning, and RLHF, which is reinforcement learning with human feedback. If you dive into AI on any level, you have assuredly run into one or more likely both of these terms. And it can be confusing as to the terminology. They do refer to two completely different things, two completely different processes, and two completely different algorithms. And they deal with different models overall. It's a different process. Like, think of RL and RLHF as two cousins of each other. Is the best way to put it. That's the most simplistic way to put it. And then so in this instance, what we're looking at on this screen as the video goes through is an example of reinforcement learning. This model is learning in this instance to play the game called Cubert. And then in this instance, I'm using a DQN algorithm with a swarm neural network in order to learn and go through this process and learn and map out this Cubert type of environment. And then so the reason why I use a DQN algorithm in this instance is the major difference between RL and RLHF. If I were to do RLHF, I would be using a PPO algorithm as opposed to a DQN algorithm. Going into these things, kind of the biggest thing that you need to know, like off the top, is that when you're training LLM models, generally speaking, you want to use a PPO algorithm. And then when you're training other types of neural networks, like say to play video games, things like that, you want to use a DQN algorithm. And then so let's start with DQN algorithms. So DQN algorithms are very specifically meant to train within discrete spaces. And so within this game of Cubert, this is a discrete space, right? We have an environment, and then there are a select number of actions that this agent can take within the environment. It can move up, down, left, or right, basically. Right, that's its actions that it can take. And then, so within this, it's learning which actions does it take. Does it go left, right, up, or down? And then in what instances does it do these actions? And then that's essentially what this model is learning. And then so while it might seem to be complex on its face, this is considered a simple problem, right? There's only 4 steps or 4 rules or 4 actions that the model can take in every single instance that we're taking. Whereas when we're talking about creating language, like natural language, what is happening within that model is it's predicting language. So it's it's a continuous problem as opposed to a discrete problem. So that's difference number 1. And difference number 2 is that, I mean, it can have to predict anything, right? We're talking about natural language. So the possibilities explode into the trillions, quadrillions of possibilities. And then so DQN algorithms, these algorithms that can train these networks on what we're looking at here, like to play Cubert, are very good at discrete problems where it's not continuous predicting, where you're only getting a very select amount of inputs and feedback about your environment, and then where there's only a few actions that you can eventually possibly take. And then it's very bad when it comes to big problems that are continuous and predicting lots and lots and lots of different outcomes. And then whereas it's the opposite is true, right? So a DQN algorithm is going to be a PPO algorithm in this particular instance. But to add another wrench into this, when it is possible to also train an LLM model to play Qbert in this instance, right? But if I were to train an LLM model to play Qbert, to play this game that we're looking at now, I wouldn't utilize a DQN algorithm to have the LLM model train. I would use a PPO algorithm to train the LLM model. And then so with that said, what's the difference between a PPO and a DQN algorithm at its core, right? Like when we're getting into the code. And then so let's dive into that. In this notebook here, I have both. I have an example of both, right? The first example that we're going to look at is an example of an RLHF algorithm or a PPO algorithm. And then in this instance, I have an LLM model. So it's a small LLM, 135 million parameter that I'm loading. So just real small model in this instance to load. I do have T4 connected. So you do want to connect T4 in this instance. You want to make sure that that's connected. And then it'll make sure within the code that you're loading to CUDA. And then once we load our model, then we're wrapping the model within this this training algorithm, this PPO algorithm, right? And then we essentially define our parameters for training on this algorithm. And then so in this instance, we are giving it a loop, right? We're giving it prompts. Explain gravity, how does photosynthesis work, and what is quantum computing? And then in this instance, I'm not giving it feedback to go back to. I'm having it give its own feedback to these prompts. But essentially what is happening is I give it the prompts and then guiding the model to answer these prompts. And then we tune the model and go through and train it 10 times in this instance for 10 epochs, right? And then so I have the model, it prompts itself, and then it generates responses based off of its prompts, and then it decodes its responses, and then encodes its responses, passes that back through its own layers through backpropagation, and then calculates its own reward. And then appends it. So PPO is based 100% off of backpropagation, right? Like if backpropagation didn't exist, PPO wouldn't exist, just flat out. So another one of these amazing things that comes out of this backpropagation, just highlighting that overall as well. And then so very straightforward, right? We train it, and then we test the model, and then we get our outputs. And then so in this instance, I've trained it for 10 epochs, and then gravity is the prompt that we give it. Gravity is a force that pulls objects towards each other. It is a force that keeps us on the ground. The Earth is a sphere, so the force of gravity is the same on all objects. This is a different response than like the general model will give you. So overall, like this was a success. And then highlighting this training, as I went through this training, right, I was going to abort this training. And I want to highlight this with regards towards the model training in this instance. So if you notice, like epoch 1 through 7, right, I'm getting these errors. And I noticed like around epoch 5, I'm like, okay. But then epoch 6, it starts going down. I'm like, okay, let me give it pause, right? Because it's not taking a huge amount of time to go through each one of these epochs, like maybe like 45 seconds each. And then around epoch 8, the error goes away. Epoch 8, no error. Epoch 9, no error. Epoch 10, no error. So essentially, like this model self-corrects, right? And then, but if you only pay attention to this, or if you were only going through this model, like I said, the bottom line, like I think 90% of people would have aborted this model training, and then this model fixed its own training, right? And then so it is like there's a bit of alchemy within this, right? Like there's a chance that you could have a model going through and 70% of the training is failing, and then it looks like it's going to fail, and then in the last 30% it comes through, like it does in this particular instance. And then so just highlighting that overall, right? But so going back up, this is a PPO algorithm, and then an example of a PPO algorithm, which we would use for RLHF training, for training, again, a LLM model very specifically. And then let's go down here. Now we have an example of our DQN algorithm, and this is kind of a souped up DQN algorithm, but so we have our Gaussian probability layer, and then I've put in, again, some kind of souped up things here, so I have like a Twistronix effect in here. I've got a noisy layer for exploration, a bunch of math, right? This is just all math. And then I've got the DQN layer itself. So this is the neural network. So like rather than a LLM model, like this is the majority of the model, right? This plus I do have a swarm algorithm element that I have bolted onto this, but for the most part, this is my model. It has Gaussian probability layers in between the connected layers. So that's kind of another kind of like a bolt-on that I put on there, right? An addition, and then so you have within this like the replay buffer is essentially how you're giving the model the data, right? So the model isn't playing Qbert in real time. It's getting it buffered by frames. So like if you're a speedrunner, like someone that's like really into these games, you're probably familiar with frame rates, right? And how frame rates work. And then so I don't know what the frame rates are for Qbert, but let's say that like every single time that Qbert moves, let's say that that's 4 frame rates. And then so what happens is that the model actually gets like in groups of frame rates, right? Like let's say groups of 16 or 4 frame rates at a time. And then that's what it's processing that data, and then it processes and then feeds back that data. So it's not 100% real time. There's a delay mechanism within that overall. And then we give it just the information about our environment. And then so in this instance, again, I mentioned I have swarm algorithms that I have bolted onto this. So this is like all the bolt-on math and logic for the swarm agents. And then this is the essentially the training mechanism. So exactly how we're training in this instance, and then how I'm training. This is a long training sequence. In this instance, is so I'm utilizing again the DQN reward mechanism, and then I'm giving it both a positive and a negative reward, and then also decreasing the amount of expiration that takes place as that score goes up. So you can see here now it's getting a score of like 550, which like, and it's exploring a lot more, like it's getting a lot higher score in this instance. So the epsilon is what's going to decrease, right? I'm going to tell it to explore less and then to rely more on its knowledge, because it's starting to understand this environment and then do a good job. Not now, right now it's just falling off as soon as it can. Of course, when we first start watching it, but in that last instance that we saw there, it was there we go. So with its last life, it learns. It seems to be learning exactly what to be doing in this instance. So I would tell it and tune it to like keep doing what it's doing with those last lives, essentially, in this particular instance. But so overall, the bottom line is that when we're training for RLHF, we're training the feedback of words on the model, right? Like we're training it on prompts and to give back prompts, right? Gravity is a force that pulls objects towards each other. It's the force that keeps us on the ground. We're training it on prompts, and the human feedback is our prompts, and then where we give it the prompts that we want it to adjust to and adjust its parameters to and its weights to, and that's essentially what all it is. It's like, here's a prompt, here's how you should be responding to the prompt, and then the model goes through and it adjusts its weights based off of that. The prompt and your adjustments essentially become like the video game, right? Like your prompt is the environment for the LLM model. It's Qbert for the LLM model, right? And then the model is going through your prompt and then figuring out exactly how to play your prompt, like which way to go, like how does it not fall off the cliff, and it's doing this same type of action and these same types of sequences, but for predicting words. And then it's just using a different algorithm behind that. So different math behind the scenes. And that's the bottom line, right? This all comes down to different math and different situations. This math, PPO math, is better in instances, in a majority of instances, when you're dealing with LLM models and you're trying to train LLM models on how to train and learn words. But a PPO algorithm is awful when it comes to training a neural network on how to play a game in a discrete environment like Qbert, and then vice versa. A DQN algorithm would be awful in this scenario as opposed to a PPO algorithm. So just highlighting those differences for you. I'll leave a link to this collab in the description of this video, and then hopefully this was a learning experience for you, highlighting the differences overall between reinforcement learning and RLHF, or reinforcement learning with human feedback. If you like this type of content, please like and subscribe. Thank you very much.